So I will just quickly show the slides again. So this is the title of the talk and the contents. And then we started talking about the purpose of uncertainty analysis. That is to show margins of error within which the data lies with a certain probability. So very often we, for instance, use the 95% confidence interval. And the red line here is supposed to be a model. And then that can, and the black line, that's the measurements. And then the gray areas would be different confidence intervals around the experimental result. And this also then relates to accuracy and precision. So accuracy being how close the measurement is to a known or accepted value. Basically, in this case, how close we are to the red line in our measurements. And precision, how close we would be if we repeat the measurements, how close we would be to getting the same result again. And that has some relation to random and bias errors, which we traditionally talk about, where precision would be more related to randomness, how close we are to getting the same result again, and accuracy, how close we are to a known value, is more related to bias errors. Okay, so you can state the general uncertainty analysis procedure in the following way. First, you define the measurement procedure. Then you identify the error sources and their distributions. You estimate the uncertainties, you combine them, and then you report the analysis results in terms, for instance, of these confidence intervals. Yeah, so I go quickly here. Basic statistics, we of course have standard deviation as one thing that we are interested in. And if you look at equations, this is closely related then to the RMS value for a sample signal. So the definition is almost the same, and numerically it's basically the same result for large N, large number of samples. And then we have the probability density function, the distribution, which is then important. So that will tell us basically the probability that we will get a certain amplitude value, for instance. And as you know, we very often assume Gaussian or normal distribution. And one reason for this is that even if the original process that we are looking at doesn't have a Gaussian distribution, if we take sufficient number of independent data, we will anyway arrive at a Gaussian distribution. But if we have not enough, then the so-called student T distribution is an alternative. So the confidence intervals states in which range the true value of a quantity will be in relation to the measurement based on the single set of measurements. So we have X, which is the measured data, mu is the true value, and then we have the standard deviation, sigma, and then we have this coverage factor K, which then tells us within how many standard deviations we are from the measured value. And it turns out that if we pick a coverage factor of 2, we get the 95% confidence interval. And then sometimes you talk about outliers, and there are, you can find in the literature, I will not go talk in details about this, but you can find advice or guidelines for how to treat this. Because if you have one value which is very far away, maybe you want to discard this from your analysis. And then you can find some information about how to do this in a systematic way. Okay, so I will say a few words about the ISO Guide to Uncertainty Management, which is a document that you can find. And it's abbreviated with GUM here. So before this, it was we used to talk about random or bias systematic errors. And they sort of abandoned this in the guide. But I think they didn't move that far. But they only describe them in terms of the measurement process from which they originate, and all measurement errors are considered to be random variables. That is, to be able to combine the effect of the two. So traditionally we use these confidence intervals for random errors, and then in the guide now they replace them by a standard uncertainty, which is a statistical quantity equivalent to standard deviation. So basically you can think about it as the usual standard deviation. But uncertainty is not considered to be just the plus and minus interval. It is instead determined for so-called A or B estimates. And then these estimates are type A. They are obtained by statistical analysis of measurement data. So for instance, taking the standard deviation of your measurement. And the B estimates are obtained from past experience, manufacturer specifications, data sheets, etc. So you can find out, for instance, that the transducer that you use has a certain sensitivity to this or that from data sheets of the manufacturer. And we will see some example later on how to apply this. Then if you have different errors, then the question is how to combine them to get the total error margin or confidence interval of your measurement. So how traditionally to combine random and systematic uncertainties. One possibility was just to linearly add them, and the other one, which is more commonly used, is to use the root sum square. So you square them, add them, and take the square root. And you do something a bit similar in the guide. So we have these two errors, E1 and E2. And then the uncertainty is determined as the square root of uncertainty 1, uncertainty 2, plus 2 times U1, U2 times a correlation coefficient. So these errors can be correlated. If they are uncorrelated, we are basically back to the same expression as above. So this is what I want to say about the guide for uncertainty management, but it's a useful document, and I think it's a good idea it can be found by searching for it and downloaded. So it's a useful document to have a look at. Okay, so if we then look at the measurement, typical measurement, we would have some input data here called XI. Then we have some kind of method. So we do something with this measurement to produce the wanted output. So in the example you've been working with now, we are applying the 2 microphone technique to the measured microphone signals. And then we get an output. You calculated the reflection coefficient or other quantities, and then we want to put confidence intervals on this output. So you need to find out the variance in the input data and F here stands for the distribution function in the input data. So there could be different types of inputs, and you need to find the variance of them and the distribution function. And then to find out how the calculation that you do is affected, you can do it in different ways, and we will talk briefly about both of them. So one is numerical simulation, such as the Monte Carlo method, and another one is called the multivariate technique, and we'll talk a bit more about this. So the multivariate analysis, basically it's a Taylor expansion. So if you have an equation for what you do in your data analysis, you make a Taylor expansion and you throw away higher order terms. So you just take the first expansion term. So this assumes, of course, that the error is rather small, so that the higher order terms, the square and the cubic and so on, can be neglected. So it's only for relatively small errors, but hopefully we want the errors to be small, so it could work for many applications. So it's sort of a linear error propagation. So one example we will see later on also for this two microphone method. Basically, this scattering matrix determination builds on this, because we do the wave decomposition for plane waves, the same as you've been testing. So in this example, we have the microphone positions, we have the speed of sound, we have the duct dimensions, we have few other inputs, temperatures, and so on. We also, of course, have, so those are examples of data that we've somehow found from experience, data sheets, well, microphone positions, you might measure them. Then we also have the acoustic pressures that we measure, and these goes into the wave decomposition first. So that's the first calculation. You do the wave decomposition and you get the waves propagating each direction, and then to get the scattering matrix, there's an extra step, a matrix inversion or calculation step. So there are two steps there where errors could be, the effect of errors could change, or the errors could be enhanced. So you do a Taylor expansion for the analysis in each step. And then this linear uncertainty analysis, the multivariate analysis, is valid when certain conditions are satisfied. So if you talk about the stacked application, for the plane wave range for low frequencies, it can be used. But if we go for higher order mode measurements, such as those Mats talked about earlier, then it tends to be too difficult, and you have to resort to numerical techniques. And one guy who analyzed this was this guy, Luc Perlings. He presented a thesis with us at KTH 2017, where with this title, so you can find this reference if you look at the KTH archives. He was also actually a fellow in the predecessor of Polka called Tango. And well, his story is maybe interesting for you, because he started off with a plan to do a certain topic, which has to do with the virtual flame model for thermoacoustics. And as a startup to this, he was supposed to do an experiment with an area expansion in a duct. And then he sort of got stuck in this and tried to improve the accuracy of the measurements. And then in the end, the whole of his thesis was centered around this, how to do good acoustic measurements in ducts. So it's an example of that, you might have a plan, but your thesis work might take another direction. In this case, it took a good direction because we got a very nice thesis out from Look. Okay, so you have already seen this a number of times. So the two microphone method, wave decomposition. And I've already shown this. But for this example then, how do we get information about the error? So we need the variance, the probability density function, distribution of the data, and the sources, as already mentioned, you can get it from the manufacturer data sheets. You can do measurements, and you could guess, make an educated guess from previous experience or so. So this is an example how to get it from the data sheets. So this is for instance, for the microphone cartridge, there's information from the data sheets from the B&K microphones that we used. And then you see this estimate type. It says B here. You remember these were from data sheets. And the Nexus is a signal conditioning system that was used, so that you can also find some information from there. And here in the final column, this is from Luke's thesis. He tried to summarize the component uncertainty that you could get from these different sources of error. And the last one here would be the data acquisition system. So you could do a detailed analysis and try to find the errors that you could get based on temperature or atmospheric pressure or other things in the different outputs from different parts of your system. From measurements, that could be the pressure measurements at the microphones, and then you can try to estimate the standard deviation, and using the experiments. And Luke used the techniques where he had step sign measurements, and then he used the Hilbert transform technique and so-called synchronous demodulation techniques, and all of this, you can find more information in his thesis about these things. Yeah, so then how to move on to do the uncertainty in the results. So we have this multivariate technique. And we are looking for these confidence intervals within how many standard deviations or standard errors. If you follow the guide for uncertainty management, we are the true values compared to the measured data. So then we are back to this equation, which you now have seen and used. So for this one, then you do a Taylor expansion, or you can do a Monte Carlo simulation. So Monte Carlo simulation would basically be that you randomly, within certain limits, change the values of these input parameters and do new calculations and see how much the outcome. In this case, the reflection coefficient is varied. Yeah, so Taylor-Chase expansion would mean that you take the derivative of this equation with respect to the different data that you are looking at. For instance, the frequency response function between the microphones, or the microphone distance, or the speed of sound, and so on. And then you get the sensitivity coefficient for each quantity. Yeah, so you start by defining this equation and then the sensitivity coefficients, and then you obtain the uncertainty for each data quantity, and then you combine them using this technique. Also, if you can find information about the correlation coefficients, but in many cases it can be assumed to be 0, so you just take the square of each one uncertainty, you sum them and you take the square root. Yeah, and I already mentioned the Monte Carlo simulation, so it's numerically in a systematic way varying the input data and with a certain perturbation, and then seeing how that affects the outcome. So it has to be performed many times, so it could be time consuming. So if you can do the other multivariate technique, that's obviously much quicker. So maybe you remember from the talk yesterday that me and Mats, we started out by doing an analysis of the errors in the tube microphone method. And we did actually investigate this using numerical simulation. It wasn't really a full Monte Carlo simulation, but we tried to vary the different input data and see how the output was affected. So these are errors in the impedance that was calculated based on A was errors in the microphone positions, which I call L and S, and B curve is errors in the measured pressures or transfer function, frequency response function in the amplitude and phase. And on the x-axis here you have this Ks, the separation, the Helmholtz number based on the separation between the microphones divided by pi. So if you remember, the method breaks down when you have Ks is equal to pi, when you have half a wavelength. So that's you have at the right end of these curves. And at the left end, you have the low frequency region, where in the measurements of the frequency response functions, you get large errors in the phase, meaning that the error sensitivity also goes up in this region. Yeah, then we did the second study where we included the effect of flow. So this is an example of the error in the microphone positions and the effect of flow. And based on these studies, we came up with this equation saying that you should, to be safe or to keep the error below a certain level, you should stay within this region. The smallest error is when the distance Ks equal to pi half. Yeah. Let's see. I think I'm moving on. So I have a few minutes. So now I will show some application examples. So we will, and some of this will be from Luke's thesis. And some of you might know or know of Mikko Hirschberg. He was also he's an expert in polka. He was also an expert in the Tango project, and we had a workshop, and then he said something like this quote, that every time you start with impedance tube measurement, it's 2 years of suffering, and maybe Luke had 4 years of suffering before he could finish his thesis. Of course, for Mikko, he had the ambition to do very, very accurate and precise measurement. He wanted 1 promille error in many of the experiments. And if you're happy with 10% error, then you can be a bit more relaxed. But if you want to do very, very good measurements, then you have to think of everything, all the error sources, try to analyze them and minimize them. So what Luke tried to do, he tried to have some kind of correct answer, a calibration standard. And then again, we have this accuracy, how close the red measurements are to this center, which is the standard, and the precision on nearby the different measurements are to each other. And for the impedance tube, he shows the case of a hard-walled termination, because theoretically we believe we know what the result that we should get if we measure the reflection, amplitude and phase. So we'll get some losses, but the reflection coefficient is almost 1, total reflection. So you get the same amplitude as you send in. And then theoretically there's a small phase shift. So this is what you expect to get from your measurement. This is the standard we are comparing to. And then he had the setup to test this, to investigate all the errors. So there was an excitation section with a loudspeaker, there was a measurement section and termination. So these are microphone measurement positions. This T, I believe, is a temperature probe to measure the temperature. And then he tested various ways to improve the results. So for instance, disconnecting the loudspeaker section from the test section. So notice this thing here, this symbolizes some flexible connection between the two. That improved the results. So the red curve is when the two sections are connected rigidly, and the blue curve is the case when they are disconnected. So you see you get much less variation, and again we will later on compare also this to this standard. Yeah, so the loudspeaker should be isolated from the test pipe, and it's also good to avoid, if you have multiple loudspeakers, it's good to avoid equidistant separations, because then you can get cancellations at certain frequencies. Then there's temperature variation, because look, if you do a long measurement time, remember Mats, when he talked, he said that they did some very long measurements sometimes. And then, of course, you start to think about stability. I mean, how stable are the conditions? Is the temperature constant during this time? And in Luke's case, he did stepped sine measurements and took some averages for each frequency. And maybe one measurement could take 40 to 50 minutes now. And if you just do one temperature measurement and assume that it stays constant, that could be a source of error. So here we have the average measured temperature. If you use that for calculating the reflection, then you get the red curve. To the left we have the phase. It's the phase measurement, and the blue one is if you take the actual temperature at each frequency. That means at each time, because he stepped the frequency. So a certain frequency was measured during a certain time period. And to the right, you see the variation of temperature during this measurement time, which was 100 minutes, it seems. So there was a variation of 0.8 degrees or so. So if you do a measurement for a long time and want to do very accurate analysis, you should actually keep track of the temperature variation during the measurements. The other thing Mats mentioned is optimization of the microphone positions. So to find out sort of the correct microphone positions, because you may try to measure them with the ruler, and at the table at the bottom you see the measured value, for instance 0.48, and then it turned out that the result was improved if you instead use 0.4816 and so on. So there was an uncertainty of less than 0.1 or around 0.1 millimeters or so here. And if you corrected for this, so again the red curve is without correcting and the blue curve is with correcting. Here we have the absolute value. It has some effect on the absolute value, but especially on the phase. You could imagine this because the phase is closely, to measure the phase, you need to measure the sort of the propagation between time between the microphones, you could say. So having an exact information about the distance will improve the phase measurement a lot. Yeah, so the errors that were identified were vibrations induced by the loudspeaker mounting, microphone positions and temperature variations, and that improved things quite a lot. But still, correcting for all of these errors, there was still some remaining problem, it seemed. So here, for instance, we can see also introducing confidence intervals. So the light blue is a 95% confidence interval, and the black curve is the calibration standard, the theory. So you can see that for the phase, which is on the right, then the measurements but the calibration standard is within the confidence interval by quite a far margin. So this result is fairly okay. But for the amplitude of the reflection coefficient, there's still some kind of extra losses or so which are not yet accounted for, because the blue curves are basically all below the calibration standard curve. Yeah, and then other possible theories was it the microphone impedance itself? You know, you stick microphones in the duct, and then you assume the duct is hardwall, but the microphone diaphragm has a certain impedance, so it's not really a hardwall thing. So is there an effect of putting the microphones there? Then there could be acoustic structure interaction, that is the sound field in the pipe excites the pipe walls. And then something called apparent absorption. We'll get back a bit more to this. So Luke did some tests trying to investigate the effects of vibrations. He tried to suspend the duct freely instead of having it clamped to see that effect. He also has this configuration called buried, which means that he put it in a box and filled it with sand to try to damp the vibrations of the walls. And it had some effect. So this is both taking into account the influence of the microphone impedance, where we had some theory, and then the influence of vibrations. And you could see that on the phase, again, it had some influence, the influence of vibrations, for instance, but still, if you look at the reflection coefficient, you still haven't solved the problem of the extra sort of absorption that you seem to have. And then Luke was actually doing secondments. It was the rules were a bit different in tango compared to in polka, because he went to Le Mans. They were not partners, but it was still okay. He also went to DLR in Berlin. They were not partners, but he could also do a secondment there. So he did test rigs at all 3 places and looked at this remaining apparent absorption. That is sort of the difference between the calibration standard and the measured reflection coefficient. And it turned out that the Le Mans rig had the best result, and then KTH and DLR had slightly worse results. So I remember my colleague Yves from Le Mans, he was very happy with this result. They have their test rig has a fairly small duct diameter and thick walls. So at the end, there were some more theories about the possible causes of this apparent absorption. Could it be so-called volumetric losses? That is not just losses at the walls, but losses in the main volume of the fluid. There's something called the Konstantinov effect, which has to do with boundary layers on the surface between 2 fluids, basically, but it could possibly also be used for the surface between a fluid and a solid. And then the 3D edge effects, that is at the solid termination, could there be some strange vortices or other things created in the corners? And then the wall roughness related losses, that the walls are not completely smooth, could also be a candidate. And well, to make the story short, the investigation showed that the 3 first, the effect of these seemed to be too small, but the wall roughness could possibly be the cause for the extra absorption. Yeah, let's see how I'm doing for time. I will show one for last example. It's just a couple of more slides. So this is also from Luke's thesis work. Because as I said, he was supposed to do this virtual flame, but as part of this flame holder, there was an area expansion. So he should do some experiments to analyze the aeroacoustics of the area expansion with flow. And for this problem, also there are the different theories for what happens in the sort of flow interaction problem at the edge. So it was interesting to do very good experiments to be able to compare this to the theories. So he did scattering matrix measurements on this configuration. Setup looked like this. So similar to what I showed before, just that he had also now microphones and temperature measurements on each side of the area expansion. There was also a flow coming. And well, this is a result showing errors, you could say, and the effect of different input data. So T, the light blue, would be temperature, RH would be humidity, the XA and XB, the green ones, would be the microphone positions, PA and PB would be the pressure measurements, and then these were all obtained with the multivariate technique, and then there was also a Monte Carlo simulation with all of these errors, which is the dashed line. So you see in this case that the total of the multivariate amounts to the same kind of errors as the multivariate, but you can also study the effect on different parts of the scattering matrix and different elements. So it's configured the same as in the scattering matrix, the 4 components. And there's slightly different influence of, for instance, in the reflection coefficients, the sort of diagonal ones, the temperature and the humidity has much larger effect compared to the transmission ones, where the, for instance, the microphone position are more important. Yeah, this one, that one I think was without flow. This one is with flow. So it contains similar type of information. Here you also have U, which is the flow velocity. And also I think dA and dV, these are the effects of the microphone, the diameter of the duct. Okay, so you see that the influence of the diameter of the duct plays a role here also, on the, especially in the transmission coefficients, to have exact information about this. And the final slide, just to show that it's useful to have this kind of analysis, to try to look at comparing with theories. So there are 3 theoretical results: Bodén, Koyman, and Susanne Boy and Bodén Nilsson. So it's a KTH work. It's the orange curve. So you see on the upper side we have a comparison between measurements and absolute value of reflection coefficient. And for this one you see that the measurement seems to be closest to the Oregon, and the low one is the transmission coefficient, and the Boy and Nilsson result is a bit more close to the experimental result. This was the final slide. This is from the same analysis. This is the so-called end correction, which is part of what you can find at the area expansion. And as function of a Strohal number now, so it's 2 times pi times f times the radius of the duct, and divided by the flow velocity. And here we see that the measurement seems to agree fairly well with the Boy and Nilsson theory. So this was just to show that it's important to make these accurate measurements to compare to theory. Okay, so in summary, we talked a bit about basic statistics. We talked about the ISO guide to uncertainty management and differences with traditional uncertainty analysis. Then how to estimate uncertainty input in the input data. Then how to do the uncertainty in the propagation using the multivariate techniques or numerical simulations, Monte Carlo, for instance, and then some application examples. So this is it.